Prof, now you can share.
Okay. All right. So what we did yesterday was material from this slide right here. We went through the potential outcomes notation. We went through randomization, and we went through randomization inference. I'm going to skip the causal models so that we can kind of dive into. Yesterday was so theoretical and laid the foundation for everything that's going to follow. What we're going to do today is we're going to get into the regression discontinuity material. And if we have time, at the end, if I cover all of the regression discontinuity, I either will start instrumental variables, or I might back up and cover something that's a little lighter and a little bit might be a nice way to end the day. I might cover my hidden curriculum material about programming. So let's talk a little bit about regression discontinuity. So regression discontinuity is a very popular type of research design. It was started in the 60s by a psychologist named named Donald Campbell. He invented it and would publish papers on it in psychology, educational psychology, usually with his grad students, but nothing really ever came of it. Never seemed to get much notice. He eventually moved on from the estimator, but he's the one that first kind of began to work on it and started to see its value. It would not get rediscovered until the late 90s. There was a brief period of time where an econometrician was working on regression discontinuity design, but my understanding is he never published on it. That was in the 70s, I think. So the first time we really see it break out is less in the theory world. It's in the applied world by very prominent economists, Josh Angress and Victor Levy, in their Maimonides rule paper in the Quarterly Journal of Economics, and Sandra Black's dissertation and job market paper on schools and the value of schools as it relates to children educational quality. So it became incredibly popular after that. Here you can see sort of the popularity. This is Campbell right here, and it just really, there is not much activity at all from the 60s to the 80s. There's a little bit. I mean, so there's like a tiny bit of activity using the method, but it's very, very small. Then when Victor Levy and Josh Angress come out, a little bit of a jump. That year, there's a few papers using it. It kind of stays plateaued. And then starting in the early 2000s, it just rises at an increasing rate, and it's just continued to rise. So it's become a very popular design in all of economics and really all of the social sciences. All of the social sciences have come to just really value this design, thinking that it provides a lot of usefulness for estimating causal effects with observational data. And many people consider it to be the most convincing of all of the designs, the most compelling of all the designs. So here's a picture of the, that's really common. This kind of picture is very common in a regression discontinuity design study. Pictures in general are very common in regression discontinuity design. And so the first thing to notice, is, let's look at a couple of things. This here, let's look at the title here. This is a study about going to college. This is the study about going to the flagship college. And the flagship college in the United States, the flagship is usually the best public college in the state in the US. All right, so in Florida, it's the University of Florida. In Texas, it's the University of Texas. In Georgia, it's the University of Georgia. All right, so it's an extremely selective. It's usually selective. High quality students enroll. Historically, at least relatively speaking, higher quality students enroll. All right. So what Mark Hoekstra is interested in, this is a paper by Mark Hoekstra in the Review of Economics and Statistics. What Mark is interested in is Mark wants to know the causal effect of attending the flagship state university on earnings. That's what he wants to know. But he can't just compare people who went to flagship schools to those who didn't because of the selection bias. Remember with the STO, AT, selection bias. So he can't just compare. Groups of students that go to flagships to those that don't, if there is differences in potential earnings for the two groups of students had they not gone. So in this case, selection bias is expectation Y0 D equal 1 minus expectation Y0 D equal 0. Okay, so this will be a bit like this. Flagship minus expectation Y0 non-flagship. So if the average earnings Y in a world where neither student attended the flagship is different, then you can't just compare the two because that has selection bias. So Mark Hoekstra needs a quasi experiment where the selection bias associated with flagships is minimized, right? Or even 0. Okay, that's what he's looking for. He's trying to find a situation. So he has an idea of how to find 0 selection bias. It's in the way that the University of Florida admitted students into the school. Okay, that's what he's going to do. He's going to use a rule. It's a rule that the university used. All right, so let's look at the rule. All right, so we've got here, that's what the study's about. Let's look at what we have here. We have the enrollment rate. Okay, so we have the enrollment rate. This is the percent. This is the enrollment rate is the percent of applicants who ultimately enroll at Florida. This is at University of Florida. Okay, so it could be anywhere from only 10% of people that apply ultimately enroll to everyone. All right, so that's the enrollment rate. And this is the SAT score. All right, so let me tell you a little bit about the SAT score. College admissions in the USA is partly based on standardized test scores taken in high school. There are 2. The SAT scored 0 to 1600, and the ACT scored 0 to 36. Mark will focus on the SAT. All right, he's going to focus on the SAT. Notice the score is ranging from negative 300 to 350. SAT scores are from 0 to 1600. So what do you think he's done here? Why is it negative? Anybody want to guess why it's negative? Why is SAT points negative? Does anybody want to take a guess?
Yes, I can make a guess. Is it because he used the said score?
He used the what score?
The said score, X minus mean over standard deviation.
No, that's close though. That's very close. What he's using is Florida's minimum SAT score is 1200. Okay, so that's the minimum SAT score that they'll let someone in, and that is a 1200. So what he did here, what he did was he made a new score. And it was equal to SAT score minus 1200. All right. So if you got a 1550, if you got a 1550, then you were right there. Right. If you got a 900, you were right there. So what he's done is he's admission cutoff. Yes, thank you, Sasha. That's right. It's the admission cutoff.
Huh?
So what he's done is he's just what Mark did is very common in RDD. He recentered the data so that at the cutoff, the variable that determines the cutoff is set to 0. All right, that's all that he's done. Okay, so it makes it a little bit visually easier to understand. Okay, so he's got this enrollment rate. He's got people. All these individuals are in this data set, and all these individuals are in the data set. Oh, excuse me. And what is he going to do with this data? All right, so let's look at what he does. So he's got all this, he's got this SAT score, he's got this enrollment rate. Now we've got these circles. So what are these circles? Apologies that this is making such large arrows. Okay, so look at the circles. So we've got here circles. We've got about 20 circles, here. What is a circle? Do you want to guess what a circle is? Let's see, I got a comment. Oh, correct. Individual score session. It's it's individual scores. It's each circle represents a group of students whose score is around that number. The circle is the average score for the group of students. Well, actually different than that. It's the average enrollment rate for the group of students with scores around that normalized SAT score. Okay, so here we see right here, let's say that for students with a score of negative 25. So that would be, full score, 1175. Recentered score, -25. Okay. For students with a score of -25, average enrollment rate is just under 10%. Right there. Let's see, I got somebody in the chat. Okay, so that's what these all are. These are just the enrollment rates along the running variables. So this is just, so all 25 or all 50 circles of the entire graph are the enrollment rates along the SAT score. All right, but notice right here. There's a big jump, a large jump at normalized score of 0. There's a large jump at normalized score of 0. Goes from 10% to 50%. Jumps from 10% to 50% at 0. Never jumps anywhere else. Just at 0. Why? Why do you think it jumps at 0? Anyone take a guess? What is 0 again? What happens at 0?
It's right at the curve, and people maybe relax when they got good score and doesn't do much to improve.
Yeah, exactly. So what's going on here? What's going on is, there is this distribution of performance. There's this distribution of performance, and it ranges from -300 to 350. But once the score hits 0, suddenly schools let them in. That's all that it is. They let them in. They're just they had a rule about where they were going to let students in, and they chose this number 1200. Okay. And then once they get to 1200, they let them in. Correct. Admission cutoff and minimum SAT score. That's correct. Okay. So you've got this. Let's review what we have here. So what we have here is we have data on thousands of high school student applications to the University of Florida. Okay. We've gotten this data directly from the school. Okay, so they gave us this data. We needed all applicants and their SAT scores, whether they attended. Okay. Once we have that, we plot a graph like this in order to show the jump in the probability of attending Florida if you have the minimum SAT score required for admission. Now, they still will let people in. They still will let people in with scores less than 1200, but those are going to be much less common. Much fewer of those end up getting let in. Some sort of needs-based criteria, or maybe it's athletes, right? And then what we also have here are these lines. Okay, last point, the curvy lines. What are these curvy lines? What are they? Anybody want to guess? what are these curvy lines?
Moving average?
Yeah, they're OLS fitted lines using polynomials for the prediction. So these are regression predicted values. These are predicted values of SAT scores, of enrollment rates along SAT scores. He probably ran a thing like this: enrollment rate equals A plus B SAT plus B SAT squared plus B SAT cubed plus X plus error. And then he gets, predicted enrollment rate. And then he just plots predicted enrollment rate against the SAT score. And because of these polynomials, it'll be flexible. It sort of flexibly moves in here. Because it looks like it's at least a cubic, because even though that's like a quadratic right there, this one appears to be more of a cubic, right? So it looks like he at least has a third order polynomial in the graph, right? So these are kind of the elements. These are kind of the elements of an RDD graph. One, there's a degree to which we see the raw data, even though it's been with mean values for the y-axis. It's still the raw data unadjusted for covariates, right? That's what he's showing. Two, then we're going to see this vertical line at 0 representing the cutoff. Okay. 3, we're going to see circles showing the means, the mean enrollment rate along the SAT score. And then 4, we're going to fit the circles with a flexible regression line. Okay, that's what we're going to do. And maybe we will put a label on this graph showing the size of the change in enrollment at the cutoff, right? Which he does here when he writes up here, estimated discontinuity 0.388. And that's right there. Okay, so that's right there. That's the estimated discontinuity of 0.388. Right there. All right. So what we've got here, turn to the point. Yes, to both of those. That's both are correct. It's the trend of the average probability. It's the trend. It's just that it's fit with regression lines usually. But yes, you could do it with a moving average. The only thing is if you did it with a moving average, looks like the thing I want to point out here is notice it appears that Mark fit 2 lines, not 1. He fit the data to the left of the SAT score cutoff, and then separately he fit the data to the right of the SAT score cutoff. So it's not one line fit through the entire. That might look like, if he had fit one line, then that might have looked like this, right? He doesn't do that. He instead says, take just this data here, right? Fit a line. Take just this data here, fit a line. That's what he's doing. Okay. So he's fitting 2 lines. And then he's comparing the 2 lines, here to here. That's what he's doing. He's comparing the 2 lines here to here. All right. Why is he doing this? So what? Why is he doing this? Mark wants to show you that when students' scores meet the cutoff, there is a 40% increase in the percentage, 40 percentage point increase in enrollment. And the idea here, and the idea that Mark wants to persuade you of, is that at the SAT score of 0, the students to the left, students just barely to the left, and the students just barely to the right are probably on average identical to each other because of the arbitrariness of the cutoff. Probably there is no selection bias at 0. There may be selection bias elsewhere, but not there. That's what he wants you to believe. He wants you to believe that it's like a randomized experiment of students to enrollment right around the 1200 SAT score cutoff, normalized score of 0. And if it's a randomized experiment at 0, then we've randomly assigned enrollment to the University of Florida, and we can then examine the causal effect of enrollment on other student outcomes. So what Mark's going to do, Mark is going to link each student's name and data with state employment records 10 to 15 years after graduation, so that we can see how much money they make post-graduation. He wants to know if attending the flagship causes you to make more money, as opposed to selection bias filled correlations. Okay. And he thinks this experiment will allow him to answer that. So we need another graph, just like this one, but with earnings, not enrollment. Okay, not enrollment. So let's look. There's what we have. Notice now we have log earnings. Now, technically, it's the residual. It's a residualized log earnings. He regressed earnings onto student characteristics, then took the residuals. Okay, so this has partialed out all variance explained by student characteristics. Now he can just focus on the SAT score. All right, so that's the first thing he's going to do. He's gonna do it that way. All right, he's going to do that. Okay, then notice all the other elements are the same. So much of this graph is identical to the one before it. Circles, recentered SAT scores, flexible curvy lines. Okay, so we've got this curvy line. He fit this curvy line here off this data. Okay, so he fit it off this data. Then he did it again with this data. So again, what does he do? He divides the data into two sections, below 0 and above 0, and fits curvy lines from OLS regressions of residuals on residualized earnings on SAT scores and functions of it, and then plots the fitted values. Okay, so he's going to do that. It's going to plot the fitted values. And notice there's a gap. There's a gap right there. Okay, that gap. And that gap, what we will try to learn today is when can we interpret that gap in this picture at the cutoff as causal. Here, it would be the causal effect of enrolling at the University of Florida on log earnings, net of individual demographics. Okay, but putting aside when we can interpret it as causal, notice the interpretation. There is a 0.095 gap at SAT score equals 0. Okay, that is a 9.5% increase in earnings, approximately. So if you just barely qualified for Florida and enrolled as a result, your earnings on average for those just around the cutoff is 9.5% higher than those just below. Mark wants you to believe this is caused by enrollment, not selection bias. All right, that's what he wants you to think. He wants you to think that it's caused by selection bias. I mean, sorry, caused by enrollment, not by selection bias. So our goal in this lecture is one, when, under what conditions, well, first of all, learn more of the mechanics and the language around this graph. All right, lots of strange terms we need to learn. That's the first thing. Number two, examine the identifying assumptions. These are the beliefs that we must hold to, which, if true, allow us to interpret this gap as causal. What assumptions are these? 3, how do we do this? Using statistical methods, not just pictures. 4, how do we check for various forms of selection bias? That's really the summary of the talk today. Okay, we want to learn more of the mechanics and the language around this graph and this procedure. There's lots of strange terms we need to learn. We want to learn the identifying assumptions that have to hold. We want to learn what statistical models to use instead of pictures, and we want to check for various forms of selection bias. All right, so let's look at that. So we want to estimate some causal effect of a treatment. We want to estimate some causal effect of a treatment on some outcome, but we're worried about selection bias. You should always be worried about selection bias. When it comes to observational data, you only have reasons to believe that that independence assumption likely is going to be violated just because of utility maximization. Under utility maximization, people are going to choose treatments all the time that are directly a result of differences in potential outcomes. And that's exactly what will violate the independence assumption. So observational data correlations probably are not going to reflect a causal effect. And you're going to have to utilize statistical models to clean up the contaminations in order to estimate those causal effects. And regression discontinuity design is one such unique, narrow solution. All right. And it works if some treatment assignment, okay, college enrollment, occurs abruptly when some underlying variable X, so here the underlying variable was SAT score, okay? SAT score was the running variable. That's what they call it. So they call, Mark would have called his SAT score x-axis the running variable. It was once called the selection variable, but the profession settled on running variable instead, right? So it's called the running variable. And that right there, that C0, that's the SAT score of 1200. Okay, so you got a couple of things. You've got running variables, X, SAT score. You got cutoffs, SAT equal 1200, all right? RDD formalizes those two pieces of information to estimate causal effects at SAT scores of 1200. Okay, now it only applies, what you learn from it only applies to 1200, but nevertheless, that's what you're doing. So I've come to believe that firms, schools, government agencies everywhere, including in Africa, have running variables that are used to assign treatments to their rules, in their rules. They basically, government agencies do this all the time. Schools do this all the time. They have to take some action and they'll rely on some rule. And if a user's behavior moves above or below some rule, they'll get some intervention. So like, for instance, I was talking with, I've been using a weight loss program called Noom. Some of you on Twitter may have seen it. I've lost over 40 pounds since October. I feel great. Clothes feel great. Clothes fit again. I feel good. Okay. Now I spoke with the researchers at Noom last week, and they told me, I was listening, that if people stopped reading the online articles by 50%. So if they're presented with 10 articles a day and they're reading 6, nothing happens. But if their reading falls below 5 out of 10, they have a coach contact the user and check in with them. Okay, so even at Noom, they are using RDD types of, well, no, so they are using rules based on running variables. Here, that would be articles a day based on running variables and cutoffs, 50% of articles, to assign treatments. Here it's coach. Okay, that kind of thing happens all the time. All that you have to do really is go and speak to these administrators and just ask them over and over and over again. Just listen, get to know the administrators who run the programs at the agencies that you want to study. Okay, just get to know them and listen. Ask them questions about their jobs. Ask them questions about how they make decisions. You want to focus though on how individual units are assigned to treatment. just listen carefully, because they don't speak in economics language. You have to listen, pay attention, and figure out if they have an RDD opportunity that you can help them with. You're usually listening for running variables, cutoffs, and treatments. That's what you're looking for. But they don't know those words. So you just have to listen and keep asking questions. People love to talk about their jobs. So just be curious, kind, and considerate, and people will open up. So many really great projects in the social sciences using RDD just came from making relationships with data holders, listening closely, and entering into a working relationship with them. It just, way more people out there have these RDD opportunities and they do not know it. And even if they did know it, they don't know what to do with it. But you will know. Okay, but you will know. Right? So that's just a little something I wanted to say. So most effective RDD programs, there's going to be a running variable. It's going to assign a treatment based on some kind of what they call a hair trigger. Hair trigger would be, the cutoff once the number of articles read falls exactly below 15%, 50%, the coaches begin to contact the user. Jan Juan says, students may know the enrollment SAT requirement of different schools, so students who apply to the admission cutoff may not apply for the flagship. Yes, so that's right. So we're going to get into that. Part of what we want to understand is, how does strategic behavior on the part of users become a real problem for us in analysis? Okay, what if students, for instance, know the cutoff for Florida? What if they know the cutoff for Florida? What if they can easily pick their score? Okay, what are the implications of users being able to select where they are along a running variable, either by changing their scores or applying for it in the first place? This is built into the assumptions and the testing we will discuss. Okay, this is built into it. So that's a great question. We're going to get into that. Okay. So there's some great examples from the literature. I'm just going to discuss a few. There's a program, there's a website called Yelp that's really popular in the United States. I think it's TripAdvisor is more popular outside of the United States. Basically, what Yelp does is you will leave a review of a restaurant or firm, and they'll present the rounded score as a star. And so if you have, underlying, on average, you've got 4.5 stars out of 5, they'll just round it up to a 5-star. And if you've got 4.4, they'll round it down to a 4. Okay. And Anderson and Magruder wanted to know the effect of getting a star. Well, the problem is, if you want to know the effect, of getting a higher star on earnings for restaurants, you will immediately have problems about selection bias. Immediately have problems about selection bias. Okay. The best restaurants get higher scores because they are popular and excellent. So if you compare higher star restaurants to lower star restaurants, you are comparing different restaurants that differ, probably even if they hadn't had stars at all, right? The higher quality is unobserved and correlated with star scores. So Anderson and Magruder, what they did was they used the raw data from Yelp. So they got the raw data of scores from Yelp, and then they also got these cutoffs, 4.5, 3.5, 2.5, to construct a new running variable and new cutoffs. They linked Yelp scores with restaurant earnings. Okay. They found if you got a star, those who just barely did earned more than those who just barely missed. So much of RDD is about comparing groups of units just above the cutoff to those just below, right? Okay, so here's another one. United States targeted airstrikes in Vietnam during the Vietnam War. The government used risk algorithms that produced these risk scores, and the military would round those scores to some integer. And then they would use those rounded scores to make decisions. Melissa Dell and Querubin, 2018, used the military and political activities of used those scores to basically recover a randomized experiment where right around the scores, you're getting people being essentially randomly bombed. At the scores, there's randomness in the bombing. Away from the scores, away from the cutoffs, there's less randomness, but right at the cutoffs, there's randomness. And they're going to use that to study the effect of bombings on the military and the political activities of the communist state later. Carr, Dobkin, and Maskus look at the effect of universal health care on mortality and healthcare usage, exploiting jumps at age 65. Doug Almond and others are going to look at the effect of a child's birth weight on mortality using a particular cutoff that happens at 1,500 grams. So it's really, really common, really common. What you do need, though, in all of these have something in common. All of these have one thing in common, though. The data sets they use are relatively large. Okay, so it's like, two of them are using hospitalization records, last two. The second one is using the universe of bombings in a war. The first is using all scraped Yelp data. Okay, that one of the characteristics that I want you to keep in mind is that RDD is a data intensive procedure. Okay, it's a data intensive procedure. So the data requirements for RDD typically are really large samples. And it's probably partly for this reason why Donald Campbell's work never really caught on, because large data sets are digitized data sets, and that digitization was slow to happen. So we usually think of trends as time trends, okay? We usually think of trends as time trends, but you don't have to think of trends as time trends. Let's say that we had here SAT scores, okay? SAT scores. And, you know, here we have a trend. So notice right here, this shows trends in the SAT scores, not time. The running variable may have trends. And the more trends there are in the data, the more data you need to identify causal effects with RDD designs. Okay. So we need a lot of data. And the reason why we need a lot of data is we need to fill out the running variable, so there's a large mass at the cutoff. That's really the key problem. So, you know, if you think about for a second, this data set, right? Let's go back to this right here. We've got, you know, SAT, and we've got, you know, log earnings. All right, we've got log earnings, and we've got this cutoff. I mean, technically, we just need data there, right? That's all we really need, because mostly what we're going to do is we're going to estimate effects right there. You're just, you know, so even though the procedure is leveraging the data close to the cutoff, you can't get data sets like that. Instead, you need you get data sets with a lot of data, and it must be so large of a data set that there is large mass at the cutoff. So what that means is you're going to need a data set that's so big, right? So big everywhere that it guarantees you have enough cut at the cutoff. Okay, so you know, only large data sets will have sufficient mass at the cutoff. Okay, so you usually need, you know, thousands and thousands of observations just to get enough mass at the cutoff. So you may not even use all of the data, but you need the whole. You need large data or enough at the cutoff, practically speaking. Okay. All right, so there's two types of there's two types of RDD designs. There's a sharp design where treatment goes from 0 to 1 at the cutoff. Okay, so that might mean like maybe there's, you know, some universal healthcare coverage that happens at some age in your country. You know, younger than the cutoff, no one is eligible. Above the cutoff, everyone is eligible. Right? So that's deterministic by the cutoff. The fuzzy design is where treatment probabilities discontinuously jump at the cutoff. So below the cutoff, use was positive, and above the cutoff was also positive, but you can see a jump that happened at the cutoff anyway. Okay, so this right here, this would be the fuzzy. Okay, that's the fuzzy. And then this, sorry, that was the sharp, and this is the fuzzy. Okay, so this would be that gap right there. The gap here would be the increase in the probability of treatment at X bar, right? It'd be the gap, be the chain, it'd be the discontinuous jump. And so that right there is just capturing those people. It captures those individuals at X bar who enrolled in the program as a result of the cutoff, okay? As opposed to all the other reasons that people often use this program, okay? So it's just a certain group of people. So there's two types, sharp, fuzzy. Fuzzy is basically an instrumental variable strategy. It requires an explicit IV estimator like two-stage least squares. Sharp is not technically instrumental variables. It's more like what's called a reduced form IV. Doesn't require all the IV-like estimators. So notice in the sharp design, all right? Notice in the sharp design. Okay, so let's just focus on, Holger says you assume that randomization is produced at the cutoff value. We're going to see that, Holger, in just a moment. We're going to see exactly what assumptions we're going to be making. And in the tradition of RDD, there's two beliefs, in the tradition of RDD, econometricians have talked about the cutoff in two ways. One is they've talked about it as a randomized experiment, which we'll discuss. So, some randomness at the cutoff is assigning people a location above and below the cutoff. Could just be noise. We all tried our hardest on the test, but randomly, I got a few questions right that you got wrong. Right? That might be as good as random, right? But even if you aren't comfortable assuming randomness, you can still use RDD by assuming the potential outcomes are smooth through the cutoff. Okay, that's not a randomization assumption, but it is also enough for estimating causal effects. And we'll talk about that one too. So these are going to be the two things that we're going to kind of talk about in just a second. The thing I want to point your attention to right now, though, is let's just look at this situation right here in the sharp design. In the sharp design, along the running variable, there is no overlap. What is overlap? Overlap means along the running variable, you would have people in the treatment group and the control group. Okay, so for every value of X, I have people in treatment and control. That overlap is guaranteed by RCTs. That's why we have balance and covariance. For everything, you've got units in both treatment and control. Well, this isn't exactly an RCT. Below the cutoff in the sharp design, no one is in the treatment group. Everyone here is not being assigned to treatment. Everyone here is being assigned to treatment. Okay. Right. So what that means is there is no value of X where I have groups in both treatment and control. So take a SAT score of 1250. Expectation enrollment, SAT. So let's do it different. Let's say, so take an age of, let's take an age. Let's take age. Okay. In the US, if you are 65, you are eligible for universal health care. If you're 64, no one is eligible. If you are 65, everyone is eligible. That means no one is in the program at age 64, and everyone is in the program at age 65. You don't have people at age 65 who aren't in the program. And this matters because it means we can't compare 65-year-olds to 65-year-olds or 64-year-olds to 64-year-olds. We will necessarily have to compare 65 to 64-year-olds. So under what conditions is that comparison going to be free from selection bias? Okay. All right. So I said all that here. So that's what, so since we can't use, since we don't have overlap, we're going to have to use statistical models to extrapolate beyond the support of the data, left and right of the cutoff. We're going to have to do something like this. Okay, so what we're going to be doing basically is using the trends below the cutoff, okay, which we're all here. These are Y0 trends. This is Y1 trends. And this is going to be predicted Y0 trends, okay, predicted Y0 trends. And right here, essentially will be the cutoff. Okay, we're going to get this cutoff right here. We're going to get an estimated gap right there based on this implicit extrapolation that's done with OLS. And if we have enough data, we'll have tight predictions and we can do hypothesis tests right there. Even though right there, there's not a lot of data, we'll be using all the data to do the projection. Okay. And that's how we're going to be comparing right here. It's as though the prediction we are doing beyond the support, beyond the cutoff is almost like we are imputing data to achieve overlap. Okay, there is no data there. It's just prediction from extrapolation, which statistical models can do. All right, it's that simple. All right, that's the simplicity of it. But it's going to depend crucially on which estimator we use. All right, it's going to depend crucially on which estimator we use, because some estimators might do this. Okay, so you might have something like this right here. Say we used a straight line. Could get something like that. Could get something like that. Could go down. Could go different functional forms. So, since we are extrapolating beyond the support of the data using a statistical model like OLS, then the details of that model will matter, because not all models will extrapolate the same, depending on the covariates and the functional form and the trends in the data. Okay. So this is actually a highly parametric approach, because we have to choose the functional form ahead of time that best fits the data. All right, so in 7 minutes, let's take a quick break. We'll take a 10-minute break, and then we'll actually, let's take a 10-minute break right now. So let's come back in 10 minutes just to kind of rest, since we've been going for almost an hour and a half. We'll take a 10-minute break and we'll come right back together. Okay. All right, I'll see you in just a second. Then we've got 2.5. We're an hour and a half in. We've got 2.5 more hours. Let's see how far we can get before we get tired again. And then we will, if we get, maybe what we can do is in another hour and a half. Yeah, in another hour and a half, we'll take another 10-minute break. Okay. So here we have some notation. So what we're going to have is a treatment assignment. It's going to be a dummy. Again, we usually are working with binary treatments in the class. We're going to have a dummy that's going to go from a 0 to a 1 if the running variable passes a cutoff. So that's what a sharp design is. So we would draw this like this. Okay, so this is X. Right, so that's what that is. And you would have like that. Okay, so the dummy here, you've got, you know, treatment equaling 0, and you've got treatment equaling 1. That's a sharp design versus what we said a second ago, which was the fuzzy, okay? And what we're going to do now is we're going to define our treatment effect, and then we're going to get into the identifying assumptions that are needed to estimate that target parameter. So this is going to be our target parameter that we are trying to estimate. Okay, so it's going to be the causal effect at C0. So to define the causal effect at C0, we'll use limits. We'll use limits. All right, so let's look at the limits. So what we've got here is as X approaches C0 from one direction, as X approaches C0 from another direction. Okay, so let me sort of draw that for you. We've got here okay, so these are all observed values here. So that's Y1, that's Y0. And then we'll put in their counterfactuals here with different colors. Okay, so what we'll do, this is still, you know, Y0 counterfactual. This right here is Y1 counterfactual, right? So we still got the same situation as before, right? We got Y1 counterfactual in pink. We got observed in blue. And what we're going to do is we're going to define our causal effect. But remember, because we have no overlap, we are going to define our causal effect in such a way that we can estimate it using that definition. And since we don't have overlap, we will define a treatment effect that doesn't depend on overlap. Okay, we're going to define a treatment effect that doesn't depend on overlap. And so that's going to be here. So what we're going to do is we're going to say Y1 here. Okay. We're going to have Y0 here. All right. Y0 here, but we're using it in the limit. So we're using, this is C0. Okay. And this is X. And this is Y. So what we're doing is we're using as Y1 approaches C0, as Y0 approaches C0, okay? In the limit, we have overlap, okay? In the limit, we have overlap at C0. So that limiting point in space is going to be where we define a treatment effect parameter. All right, at that point in space is where we're going to define the treatment effect parameter. Right, so this here is the parameter, right? So this is the target parameter. And then this here will be the data. This will be the estimate, right? It's going to be the estimate of the target parameter using the observed, not the potential outcomes. Okay, so our models will be focused on this second line, not the first. The second line represents an estimate of the first line. Okay, and so right here, right there is this. That green line is the causal effect of the sharp regression discontinuity between expectation Y1, that's this, and expectation Y0, that's this, at the cutoff, which is right there. Right now, technically, remember, even at C0, there is no overlap. But this is the target parameter. Not the actual data. Okay. All right. So let's go forward. So in order to do this, in order to estimate that causal effect at that cutoff, we're going to have to extrapolate beyond the support of the data. And so let me just restate this right here. Because we have no overlap at C0, we have to extrapolate and use fitted values to impute missing counterfactuals at the cutoff so that we can identify the parameter, the target SRD parameter we just discussed. We have to use extrapolation. Okay. A lot of estimators don't use extrapolation. Difference in differences doesn't use extrapolation. Matching doesn't always use extrapolation. Sometimes it does, sometimes it doesn't. So not everything is extrapolation based, at least not explicitly, but this is explicitly extrapolation based. And it's like, it's going to have like a bit of an imputation kind of framework. All right. So extrapolation in RDD, the counterfactuals are conditional on X. So we're going to use extrapolation to estimate treatment effects with the sharp RD because we don't have overlap. This extrapolation will be our counterfactual, or it will rather, it'll be an estimate of the counterfactual. Okay, but it's only a good estimate if certain things hold, assumptions and models being specified correctly. We need both of them. So estimation methods attempt to approximate the limiting parameter using units left and right of the cutoff. Okay, so this is from Marcella Perellin's simulated random variables, dash lines or extrapolations. You can see right here, same kind of thing, extrapolation. Marcella's excellent simulation here. This is extrapolated data, equaling or estimating counterfactuals. Right here, dash line is extrapolated. But look at what we're doing. Where does the extrapolations come from? The extrapolations are based on fitting the data above. So let's say we'll look at below the cutoff. Extrapolations above the cutoff are based on fitting the data below the cutoff and predicting beyond the support of the data. So we fit the model here. we project based on the coefficients estimated below the cutoff. So if we put in polynomials, the prediction will continue to follow the paths created by those fitted polynomials, which can lead to overfitting, right? So it can lead to overfitting. So this is actually a major part of the project, getting this right, all right? So what is the assumptions that we need? You can kind of see the assumptions that we need right now in this picture, all right? What we need is, if this dashed line is an unbiased estimate of the counterfactual, then it necessarily means the counterfactuals were smoothly evolving through the cutoff from below XC0 to above. It's like, you know, you're saying basically, you're saying essentially that this would have happened as opposed to this would have happened, right? So you're assuming that it would have continued to evolve smoothly, right? This picture right here, this picture of an extrapolated line based on the XC0 data and a regression fit assumes that the actual underlying counterfactual Y0 data for X greater than C0 would have evolved smoothly anyway. Would have evolved smoothly anyway had the treatment never occurred. Okay, right? So the key identifying assumption is called smoothness, not randomization. RDD can be thought of, in other words, in two ways: based on smoothness, based on random experiments at the cutoff. These are complementary. These are different identifying assumptions with different implications. Okay. All right. So we're going to talk about smoothness. So smoothness of the conditional expected functions basically says that expectation Y0 would have been smooth. The entire function would have just continued to evolve at the same way that it had been evolving before. It would follow the same, there would be no discontinuous jump in the potential outcomes. Now, there can be a discontinuous jump as we go from Y0 to Y1, obviously, but we're saying when expectation Y0 is evolving through X, there is no jump, okay? So the smoothness assumption is going to allow us to use the average outcomes of units just below the cutoff as a valid counterfactual for units just above. In other words, extrapolation is warranted under smoothness. And if smoothness is violated, extrapolation will give you incorrect biased estimates of the values of the counterfactual. Okay, so you have to have smoothness under this framework in order for smoothness, in order for this to be this extrapolation be valid. All right, but you still have to know the functional form of the underlying potential outcomes as a function of SAT scores or whatever. Causal effect of the treatment will be based on extrapolation. Means you have to think long and hard about smoothness and what violations mean in your context. It's not directly testable because it's based on potential outcomes, because those are counterfactuals. So here's an example of smoothness. I fit this data. This is again from Marcella. I simulated this data. These are dots below the cutoff and above the cutoff. And I fit the lines here and I fit the lines here. And they touch right there. Okay, so they touch right here. Now, they touch. The lines touch, but that's only because the data generating process is a smooth function of X. So when I fit the model when I fit the model twice, smoothness ensures that the lines touch. So, but this is all, notice, this is potential outcomes. We need potential outcomes to be smooth, not actual ones. These are actual outcomes. This is actual outcomes. So remember, smoothness was here. Right? It was this stuff. It was Y0. This is Y1. Okay, and this is Y0 here. Right? And so what we have is if smoothness holds, then the gap in actual outcomes is causal. If smoothness would not have held, then the gap is not interpretable as causal. Okay, not interpretable as causal. Now, it's very common for authors to transform the data by centering at C0. And what you'll typically do is you'll subtract from the X variable the value of the cutoff. You'll subtract from it the value of the cutoff, and then you'll run your estimation off that. Now, it has no real effect on the interpretation of the coefficient when you do that. So we'll go Y regressed onto, age. So you could have had here Y equal beta 0 plus beta 1, age plus beta 2, edu. Okay, so we could add that. But then what we do is we subtract 65. Maybe that's the cut. From age. I distribute the beta 1 and I get beta 1 age minus beta 1 65. And all that ends up happening is I have this and this. This is a constant here. That's a constant and that's a constant. So I just end up with a new constant. And the new constant is here, right? So I end up instead with Y equal alpha plus beta 0 minus, or sorry, it'll be Y equal alpha plus all this. Beta 1's the same. Okay, so this beta 1 and this beta 1 are the same. And this beta 2 and this beta 2 are the same. So when we recenter, beta 1 remains the same. Beta 2 remains the same. But alpha, beta 0 becomes alpha. All right, becomes alpha. We get a new intercept because we have a composite additive, an additive composite term that becomes the new intercept, which is this. So let's see, we regress Y onto D and X. what do we get? We get, D is equal to 80, X is equal to 2, constant's equal to 100. Now we're going to recenter the data, generate XC equals X minus 140, reg Y D to X over XC, still 80, still 2, but now the constant's different. Look, constant has changed, but none of the other coefficients are different. Okay, so recentering is easy, very common, and it can help with interpretation in a regression model. All right. What about, but let's return to smoothness. What if the function of the potential outcomes is smooth, but not linear? Does that matter? Yes, it matters. All right. Yes, it matters. So smoothness is not the same thing as saying the precise functional form of the underlying potential outcomes. You can have data that is linear and smooth. You can have data that is nonlinear and smooth. But if you use the wrong model, you may get biased estimates of the treatment effect. All right. You may get wrong estimates of the treatment effect. Okay, let's look at a simulation. Again, I got this from Marcella. All right, so this is Marcella Perelian's simulated random variables. Marcella is a health economist at UC Denver. So this is his code. We're going to have here generate variable x2, generate variable x3. Okay, so this is, notice this is a quadratic and this is a cubic. And we're going to make a variable called y, which is going to have an intercept of 10,000. There will be no treatment effect, but it will be decreasing in x at an increasing rate. Okay, it'll be decreasing at x is an increasing rate, and they'll have this large variance here, and we'll do a scatter. Okay, so when we do that, look what we get. Now, notice it appears like with your eyeball, there is no jump at C0. Notice the dark circles and the gray circles are touching at C0 right here. Right? Looks like they're touching. It looks like there actually is no estimated gap. So, using your eyes, which is important, there is no visible jump. But if we fit the data using a linear model, our statistical model will find a jump. Because look, right here, right there. Notice, because the data generating process followed a quadratic, but we fit the model with a line, we inadvertently identify a jump where there isn't one. It's just the influence of the outliers on the fitted model that is causing the gap to form. It's causing the gap to form and nothing else. It's all this stuff over here, pulling it down. It's all about this mass right here, pulling it down. and this mass right here pulling it up. So if this if you could have blocked out all of this, say right there, and then did it, would have touched, right? But the problem was all this data, problem was this data does not accommodate a straight line, but this data would. What if we had fit not a line, not a linear model, but a nonlinear model? So let's look at a nonlinear model. This is the nonlinear model, right? Still linear, but look what's in here. Okay, that f of x. What is that f of x? Well, f of x is basically going to be x plus x squared plus x cubed plus x p, right? It's going to be a pth order polynomial. It's going to be a pth order polynomial. It's going to be a pth order polynomial. Historically, researchers would use high order polynomials, but as we'll see, Gelman and Embens urge us to only use quadratics if we need them. Okay. This is to avoid overfitting. Since we are extrapolating, overfitting is a potential problem. Since we are extrapolating, right? So let's try a nonlinear model. Right? So there is two ways to model there's two ways there's two ways to model this f of x. One is, like I said, use all the data and have f of x equal a pth order polynomial. That would be this right here. All right, estimate that model, and then when you estimate that model, this becomes your causal effect at the cutoff. And an alternative is to use non-parametric kernel methods. Okay, so there's basically two ways to go about it. One is global regression with pth order polynomials, and then the other is a non-parametric method with weights associated with kernels. We'll look at both. So we're going to have, if we use the pth order polynomial approach, the goal is to model the polynomial, model the data generating process with different polynomials on each side of the cutoff. Okay, so what you're going to do is you're going to assume that expectation y0 follows a polynomial. You're going to assume expectation y1 follows a polynomial, right? So this is just describing the flexible form of the potential outcomes. But we will need a regression model that doesn't base itself on y0 and y1. So we will use interactions to model the same series as above. Okay. All right, so let's look. So here we're going to go, this is going to be our regression model. And notice what we get. Just remember here, expectation y0. This right here is basically expectation y0. That right there is basically this first line is expectation y0, right? Because notice no D term. So this is the line below C0. This is the line below C0. This right here this This second line is expectation Y1. Because notice D is interacted with each X term and has its own new B coefficients. Notice X has beta 0, 1 above and beta star 1 below. Okay, so you've got here, you've got a beta 1 coefficient, and then you've got a beta star coefficient. All right, but basically what you have here is this specification. This specification is just like the graph with two lines fitted separately. The interaction is essentially fitting lines below the cutoff. That's that beta 0, 1, beta 0, 2, beta 0 P, and above the cutoff, beta star 1, beta star 2, beta star P. It accomplishes it via the interaction of the X terms with D. But the delta parameter, DD, is the estimated target parameter of interest. The rest is just trying to model correctly for extrapolation. All right, the rest is just trying to model for extrapolation. So this right here this is our estimated target parameter. This is our estimated target parameter right here. Okay, the rest of this stuff is just done for modeling the nonlinearities. Okay, so we'll see right here. Let's go back through and now let's do the same kind of simulation before from Marcella's code. Let's do the same kind of simulation as before. And now we're going to have a data generating process that's based off of X here, X squared here. X cubed won't matter. X cubed is not a part of it. We're going to put X cubed in the model, but it's going to turn out not to matter. And then we're going to do the scatter. But look at what we're doing now. Now that we're using fitted values, we've got to actually create, we've got to plot Y hat against X as opposed to Y, because now we've got to model this nonlinearity. All right, so let's see what we get. Okay, so see when we do this here, oops. Here we see that modeling the nonlinearities explicitly using polynomials gives a more credible fitted model that, you know, doesn't give the false impression of a causal effect, right? The linear model was not correct because it didn't fit the data well and therefore had poor extrapolation. It had poor extrapolation properties. Okay, so what's normally done? Let me just say one thing real quick. So what is normally done in an applied paper where people are running regressions on RDD, since the functional form specification is so critical? They'll typically report, they'll typically do this, show the data and allow the reader to decide whether your fitted values shown on the data reflect a jump or noise. Okay. Experiment with multiple functional forms, no higher than a quadratic. Although older papers often went above to cubics, etc. Okay. Experiment with multiple functional forms. Goal is to find the functional form that best fits the data, but doesn't overfit. Best fits the data, but doesn't overfit. Holger says, can you assume overlap or randomization, or can you assume both? What you typically see is researchers will talk about them interchangeably. Historically, they spoke almost exclusively in terms of as though random around the cutoff. But Vanderklau, Todd, and someone, Vanderklau, Todd, Han, it was Han, Todd, and Vanderklau, showed that you don't need randomization. Smoothness is enough. But other studies will assume randomness, and that will allow them to do randomization inference. Okay, so largely I am influenced by what I've read of Han, Todd, and Vanderklau, but there is a diversity of authors that use these assumptions differently. Okay, so you don't really, it's enough to speak in terms of smoothness, but if you're working with that smoothness, you're largely going to be estimating, you're going to be experimenting with those functional forms. Okay, so let's say we are using smoothness, then what can we do to evaluate the credibility of that assumption? Well, your main results are only causal insofar as smoothness is credible. If smoothness is not credible, then none of this is interpretable as causal effects. And smoothness is not guaranteed. In a randomized control trial, independence is guaranteed. But with quasi-experimental designs, the assumptions aren't nearly as credible. Okay, because with an RCT, you know that a coin flip is distributing the potential outcomes across treatment and control equally. Their means are the same. With smoothness, you have no such confidence. So what you've got to do instead is you've got to check to see how believable smoothness is by looking at its logical consequences. You've got to scrutinize alternative hypotheses that are consistent with your main results through sensitivity checks, placebos, and alternative approaches. And we're going to discuss some of these violations. The main challenges that you need to have in your mind when you're doing this RDD is something that was brought up a moment ago. Is it possible that someone is manipulating their running variable score they're manipulating their running variable score, and it could be that the cutoff itself is endogenous, right? So basically, both of these can be thought of as violating smoothness, but kind of for different reasons, right? All right, so let's look at the manipulation of the running variable. There's kind of 4 ways that the running variable manipulation can happen. First is if the rule that the firm or the government is using to make treatment assignments based off running variables and cutoffs, if those things are known ahead of time, Okay. If they're known ahead of time, then you might use it strategically if you're interested in getting into the treatment and if you have time to adjust. So if you know the rule, you might take advantage of it by changing your behavior, so long as you want to be in the treatment, and so long as you have enough time and you have the resources to change your behavior such that you change your running variable score. So in the SAT standardized test score, that would basically mean that someone studied extensively, took the test over and over and over again until they successfully got the grade they wanted. Melba says, how do we think about the running variable as the basis of the program eligibility? It is also the key factor that determines Y0 potential outcomes. Likely would it be the source of selection bias? How do we think about the running variable? It is also the key factor that determines Y0. Well, the thing, Melba, the thing that you're mainly, this is where this assumption of smoothness is coming in. So if you have, this right here, we'll just do Y0. Okay, so right, so this right here is Y1. This right here is Y0, and counterfactual. And this right here is Y0 actual. All right, so this is the running variable, right? And then this is Y, this is outcome Y. So how do we think about the running variable? The running variable, Y0 equals X plus X squared plus ... plus error, right? So it's, there's some positive coefficients. It looks like it's, looks like it's rising. It's got some linear function here. It looks like X squared isn't really playing a whole lot of it. So it could be like, 0 on that. This might be like a 1 on this, right? So it looks like it's just kind of fitting a line. So we could just sort of fit this in here. And, we've got that, and we have this. So what we've got here is Y is a function of the running variable. What we need for identification is that it is really nothing more than smoothness in Y0. That's all we need. If we have smoothness in Y0, then the change in treatment that occurs at C0 will allow us to identify causal effect at C0. Okay, so even though Y0 is based on X, that doesn't create a problem for us so long as that's true. So long as that is true. If that's not true, then it'll create a problem for us. Angelica says, can time be used as a running variable? Time is very often used as a running variable. There is some papers suggesting that it's kind of a little bit more complicated than it appears to be. I probably need to start expanding my, my discussions of time as a running variable. But yes, Angelica, many people will use time as a running variable. I can point you to some papers that will give you some guidance on using time as a running variable. But yes, you can do that. Can we see the running variable as a confounder? It's funny you say that. I skipped this. But essentially, this is the running variable. And yeah, it's a confounder because basically X is determining Y and it's determining D. And so what you've got to do, and it could also be that, you know, X is endogenous to something that's causing, you know, something else. So there could be some sort of endogeneity. And what essentially is done is essentially to block on X using the cutoff. But the problem is, so you can do it. You can address it as a confounder. It's observable. So, you know, the running variable is an observable confounder. Okay. But the nature of the data is such that we can't just control for X because of the lack of overlap. So we use these models for RDD to handle the fact we can't satisfy overlap, right? Because without overlap, we can't identify a target parameter. So we use that limiting target parameter, right? But yeah, you can think of X as, but yes, X is a confounder and it's observable. That means RDD is a selection on observables problem. But you use these functional form solutions to isolate causal effects. Only at the cutoff. Can't do it anywhere else because only at the cutoff is there a change in treatment status, right? Whereas ordinarily with overlap, you have changes in treatment status all along the X variable. You know, yeah, you have it everywhere because you have units in treatment and control for all values of X under overlapping types of problems. But in RDD, you don't, because the boss uses C0 to make decisions about which units get treated. But now we need to figure out, you know, this main challenge. So let's look at this first one. All right, test one. Can we test for whether or not people are endogenously choosing their running variable score, right? Is there something we can do? Is there something we can do to check whether or not people are choosing their running variable score? So assume that there is some desirable treatment, okay? And then you have some rule that when the running variable exceeds the cutoff, individuals will sort into treatment, not by choosing the treatment, but by choosing the value of their running variable. They'll choose the grade that they got on the SAT score, okay? And by choosing the grade, they either get into the University of Florida or don't, okay? That would basically mean people are not just doing their best on these tests. They're strategically trying to get just enough of a score to get in. If that's what they're doing, we say that they are manipulating the running variable, or we say they are sorting on the running variable. That's the phrases that you'll read. They mean the same thing. So imagine there's some like healthcare intervention, all right? A statin that's being used to treat heart disease. There's a randomized experiment. All right, I want you to imagine a randomized experiment with a treatment for heart disease. And if you get the statin, it's believed that it will extend your life several years, right? And if you don't get the statin, then you'll die from heart disease at whatever age you were going to anyway. Okay. Let's say everybody knows this, everybody believes it works, and everybody wants to get the statin. But only the people in one room, room A, are eligible to get the statin. So 100 people are assigned to room A, 100 people are assigned to room B. Let's say everybody knows that room A has the statin. Everybody wants to move between the two rooms. Everybody has time to move between the two rooms. If we start at 100, here, I'll draw this. Let me do one thing real quick. Okay, so we got 100 people in both rooms, before. Okay, how many people do you think will be in room A and room B after? If you had to guess, how many people do you think are going to be in room A? If people can move between rooms. Somebody want to guess? What would you do? What would you do if you were in the control group? What would you do if you were in the control group? You had heart disease, and you knew that if you could just get the statin, you could extend your life. Would you move rooms? Yeah, move, go to room A. So it would look like this, right? It would look like, right? We would expect, if the treatment is desirable, they want to move, they can move, we would expect them to move. But think about what the data would look like if this happened. You'd see a discontinuity in observations at the cutoff. This sorting on the running variable problem actually makes testable predictions. We could check the density function to see if there is a spike in the number of individuals at the cutoff, C0. If there is a discontinuous jump in observations, i.e. the density jumps at C0, then it suggests sorting on the running variable. It suggests sorting on the running variable. And that is a test that was developed by Justin McCreary in the Journal of Econometrics in 2008. It was a density test to test for sorting, and it's become basically mandatory in the literature. So you can't test for smoothness, but you can start to test for phenomenon that are suggestive that smoothness isn't holding. And any kind of violation of any kind of sorting has the potential to break smoothness. So assume a null. Here's how the density test works. Assume a null where the density is continuous at the cutoff point. The jump will demand explanations if continuity is typical. Under the alternative hypothesis, the density increases at the cutoff as people sort into the desirable side of the cutoff. It's going to be oftentimes visualized with confidence intervals, illustrating the effect of the discontinuity on the density. You need there to be no jump at the density. So the steps, there's going to be software that does this. So let me just kind of walk you through what all of this software does. It's going to take the number of observations. So this would be like the number of students. And rather than having a circle representing enrollment rate, it would be a circle representing the number of students at a particular value of the running variable. Okay, so that's what this would look here for our example. Count number of student applicants at bins along the running variable. Okay, you may have to experiment with different bins. Okay. Secondly, you want to estimate your nonlinear model. Probably before this even, plot your data and then choose a specification, probably nonlinear, to estimate the density model. It'll be likely a regression. It'll likely be a regression model with flexibility of modeling X terms. And then last, do a hypothesis test at C0. Can you reject the null of no jump at C0? That's what you're going to do. So density tests are mandatory for every analysis using RDD. You can do it lots of different ways. You can do it manually yourself if you're comfortable doing it yourself, or maybe that makes you feel more comfortable to have more control over the programming. You can do it. It's a simple procedure. As long as you're able to calculate conditional expectations, you can do this test. Okay, you just need observation. You need a running variable. You need to have a number of observations along the running variable. You can download packages that'll do it. There's one that Justin McCrary wrote called DC density, or you can use the RD density command or even the RD plot command. So a discontinuity in the density is suspicious because it suggests manipulation. Smoothness might not hold. All right. Technically one doesn't need a smooth density for smoothness, but this is as good of a test as we have to provide some suggestive evidence that we should be worried. Density tests are not helpful for RD in time, according to Hausman and Rapson, which is an entirely different subject that Angela asked about, and I need to update these slides. I haven't taught RD in time before, but I need to, because it comes up a lot with seminar participants. So here's an example. These are both densities. And notice what you're doing here. You're fitting, okay? You're fitting a model with OLS, all right? So this is like some sort of OLS model, Y equal A plus income squared plus income cubed plus E, right? Where Y is number of observations per bin. Okay, so you bend it. Melba says, is it possible for the sorting to be due not to strategic behavior, but because X is a function of several variables and due to variable weights, there's a sorting? Yeah, Melville, that's true. That's going to be the second situation I'm going to describe in just a second that I think is more what you're describing. It's called heaping. It's not due to strategic behavior of it's not necessarily due to strategic behavior of the person. It can be something like a rounding tendency or some sort of weighting procedure, but it can have the same problems. Problems are going to be a little different, and the solutions are a little different, but I'll talk about that in just a second. Right. So we've got here, we do a test right here. We do our hypothesis test, no jump at C0. We see if we can reject it right here. No jump at C0. We likely reject this null because visually I can see the jump. For some reason, there are a lot of people who make just enough income to qualify for this program. Right? See that? See how there's a lot of people there versus right there. Okay. So it looks like what happens, it's looking like what's happening is a person is either reporting income incorrectly to just become eligible for this special needs program, or they're working less in order to be eligible. Holger says, how does sorting break smoothness? So Holger, it actually is not, so, it's a special situation where sorting can break smoothness. If the individuals sorting have very different potential outcomes, then the sorting is removing those potential outcomes, which can cause the counterfactuals to artificially shift just at the cutoff. So it really is sorting and the values of the potential outcomes of those sorting individuals. It's really whether or not the people that are sorting have potential outcomes. So it's like you're pulling those potential outcomes out of the counterfactual and placing them somewhere else. And as you begin to move those units around and they're not there in counterfactual, then the inference ends up being violated. So it's just going to be really a matter of what is happening, what the value of the potential outcomes are of those individuals that are shifting. So this is an interesting study. I don't know if anybody on the call has ever run a marathon. I've run 2 of them. The first one I worked really hard, trained for a long time. I'm not a fast runner and I'm not very athletic, but I had a really good time in the marathon that first time. And I run pretty slow. I run a 10-minute mile when I'm running marathon distances. When I'm running shorter distances, I can run 8-minute miles. And on the day of the race, I had so much adrenaline that I thought to myself, I think I'm going to be able to make it. I think I'm going to be able to run my 8-mile pace. And even though that would have shaved off 2 minutes on my average mile, and I'm going to be able to get under 4 hours. So if I run, at a 10-minute mile, you run a marathon in 4 hours, 20 minutes. Okay. But I wanted a sub 4-hour marathon time. So I had to speed up, but I had never run that fast for 26.2 miles before. Okay. I had never run that fast before, but nevertheless, I wanted it. I was eyeing the time. Okay. Second time I ran a marathon, I didn't train whatsoever. And I got, actually, I came in second to last place. It was me and this extremely elderly man who had trouble walking. And I came in second to last place. I barely beat him. It was a horrible nightmare. And I ran the race in, over here. That's where I was. Versus, right there at my 10 minute pace. Okay. So what ended up happening? Well, I was running 8-minute miles for about 18 miles. And then I started to slow down. I felt like every bone in my feet were broken. And I ended up finishing the finish line at exactly 4:20, literally exactly 4 hours and 20 minutes. I couldn't beat the 4-hour time. But the fact that I was trying to is really common. It's really, really common in marathon running. And you can see that here in a paper by Allen, Desho, Pope, and Wu. Allen, Desho, Pope, and Wu. And what they do in this paper is they take all 9 million marathon finishing times for lots of different marathons, okay? And they plot the data. And you can see from the data, it does not appear to be that it's smooth in the density. Okay, so this is number of finishers, all right, number of finishers in some sort of really small bin. All right, so this is probably like, 1 minute bins. And you can see right here that there's jumps. There's jumps at every half hour. It's not smooth, then it kind of disappears here. There's a little bit there. Over here, there's not one. So what this suggests is, people aren't running as fast as they can in the marathon. Not everyone. Some people have target times, usually 30-minute intervals, okay? Especially breaking the 4-hour barrier like I wanted. That's the biggest one. And what they did was, as part of their analysis, they ran McCrary density tests on the density at each of these 30-minute thresholds. Okay, and you can see that right here in blue. And so in blue, what we see is here, we'll just, right? So the McCrary density test greater than 0, 150, 25, 75. Now it's getting smaller. As we get over here, it's getting less and less significant. Okay, so you're seeing right here these Z statistics. The Z statistic on the McCrary density test is one of our statistics to tell us whether we rejected the null of of smooth density at C0. Okay. Now we get into this second form, and this is what Melba was asking about. What about violations of smoothness, smooth densities that aren't exactly due to strategic behavior by people? What if there's some other process violating smoothness of densities? We'll look at one important one called non-random heaping. Non-random heaping along the running variable. Right? And we'll use this example from a paper by Doug Almond and co-authors. Now, there was a paper published in the Quarterly Journal of Economics. There was a paper published about premature babies receiving medical spending and being more likely to perish. Okay, so there is a very strong positive correlation between a newborn having expensive spending on her at birth and her likelihood of dying. The more spending by the hospital, the more likely she dies. This is not causal, because the hospital is spending money on babies that are almost about to die anyway. They are born premature or with development problems, and the hospital spends money to save them. But is this spending causing health mortality to fall? Right? Not, it's positively correlated, but it might be causing mortality to fall. They'll use RDD. Okay, they're going to use RDD to test. Right? You got the severe selection biases group's going to use RDD to answer it. We need a cutoff and a running variable. The running variable will be baby's birth weight in grams. The cutoff will be 1,500 grams. The reason the cutoff is 1,500 grams is because at 1,500 grams in American hospitals, doctors will move a child from their mother's room to the intensive care unit, a special room where the child receives intensive medical treatment, but it only is triggered by weight below 1,500 grams. So 1,500 grams is the cutoff, and birth weight is the running variable. Okay. So sorting is only a problem when it breaks smoothness. Yeah, sorting violates smoothness. If it's not violating smoothness, then the extrapolation you're doing is still estimating the counterfactual. So, you know, if you can hold smoothness, then you will be able to estimate causal effects at the cutoff. It basically means that whatever is going on with the sorting, it's not violating smoothness. So you have to think a little bit more about what that does mean, but it technically doesn't have to violate smoothness. I think that it's often thought that it probably would violate smoothness, but it's one of the, since you can't test that directly, it's kind of an auxiliary test that people use to see if smoothness is likely violated, even though it doesn't have to be violated by that sorting. So Doug Allman attempted to estimate the causal effect of medical expenditures on health outcomes using RDD. In the United States, newborns whose birth weight falls below 1,500 grams are placed in intensive care. 1,500 grams is considered to be a very dangerous environment called very low birth weight, where a child has a higher chance of dying. They're going to compare those just above 1,500 with just below using hospitalization records. They found that a 1-year infant mortality decreased by 1 percentage point just below 1,500 grams compared to just above. They conclude that these medical expenditures are cost-effective, compounded value of life over a typical lifespan, because the increase in survivor that happens just below 1,500 grams is about 1 percentage point. When you multiply that over an entire lifetime, it's the value of that life is far, far higher than the cost of the medical expenditures. But let's look at the density tests. So this is the density test. I want you to look closely at this. Look what we have. Okay, we see strange pattern in the data. These are observations, not mortality outcomes. Okay. At some regular interval, the spacing between these lines looks identical. At some regular interval, there is around 20,000 infants with exactly that weight. It is improbable that females give birth to babies with birth weights distributed, with these modes every 50 or so grams, right? Something else like Melba's comment is probably going on. What? Well, this data comes from a lot of hospitals. This is the NCHS data set, all births. We have all birth certificates from 1983 to 1991 and 1985, 2003 from hundreds or thousands of hospitals, some of which are poorer than others. Some hospitals have very primitive scales compared to others. Some places appear to be rounding, and others appear to be recording accurate weights. If the places the places rounding have different mortality outcomes than those who don't, it can introduce a separate problem. Because at the cutoff, it's no longer smooth. All right, so look, this is what's interesting is that Doug Allman rounding off. Yeah, is that not a phrase that, so rounding off would be, so rounding, I don't know if that, rounding in the United States anyway, rounding would be this. A child is born 25 grams. At a poor hospital, maybe the scale is only measured in, maybe the scale doesn't get that precise and records it as 1,500 grams. Or maybe at those hospitals, nursing staff just rounds down to 1,500 grams, but not every hospital. So it doesn't appear remotely believable that all of the babies in these 20,000 baby bins weigh exactly the same as each other. More than likely, their weight is near that number, and someone or something recorded a weight that was exactly at that rounding interval. That's what's likely is going on, because there's nothing biological about humans. There's nothing biological about humans that would get you see how look at it, it's the same everywhere. That's just not possible. So something's going on. Okay. So the picture shows heaping, which is excess mass at certain points along the running variable. Technically, this and this, right? So right here, look at this one. That's like that picture. Notice, there's only a break. It's not a heap. It's just a break in the density. The McCrary density test was designed. McCrary density test was designed for breaks in the density, not non-random heaping. Okay, not non-random heaping. And the reason is because with the McCrary density test, what the McCrary density test is going to do, is it's going to fit all of this data. So it's going to use all the data to fit this line to become a high-powered test so that it can have a chance to reject the null right here, right? So it's using all of these observations, okay? But when you do the same thing with a McCrary density test off of non-random heaping, you get something more like this that happens. This ends up being the fitted value. And McCrary density tests have a hard time of detecting breaks, even though they are visible with the naked eye. And that has to do with the sheer number of observations influencing the fitted lines at each of the equally spaced intervals. So McCrary will not reject. The authors used a McCrary density test and failed to reject the null, even though you can see with your own eyes massive heaps of data at regular non-random spaces. Okay. So in Monte Carlo estimates, so in this case, the heaping that was there, the babies, it just so happened that the babies at the cutoff had very high mortality rates. So all the inference done using those observations were contaminated by selection bias. Okay. Alan Barreca et al. Write this. So they're a team that critiqued the Doug Allman paper. They say this heaping at 1,500 grams may be a signal that poor quality hospitals have relatively high propensities to round birth weights, but it's also consistent with manipulation of recorded birth weights by doctors, nurses, or parents to obtain favorable treatment for their children. Barreca et al. Show that this non-random heaping leads one to conclude that it is good to be strictly less than any 100-gram cutoff between 1,000 and 3,000 grams. In other words, they repeated the Doug Allman et al. Analysis using every 100-gram threshold from 1,000 to 3,000 grams as though it was a real cutoff. And they always found the same thing. At those fake cutoff heaps, you were always better off to be born 1 gram below the heap than at the heap. Okay. Even if those 100 gram, even though those 100 gram thresholds have no treatments associated with them. Okay. So what can you do? What can you do in this situation? So you can do what's called a donut hole regression discontinuity. And a donut hole regression discontinuity is going to compare the averages as we approach C0 from either direction, but we're going to drop the data at C0. Because the idea is, just remind ourselves what the idea of RDD is. Our idea of RDD is that the cutoff okay, so the idea is that the idea of RDD is that in the limit, smoothness holds. So it should be relatively insensitive to dropping units at 1 bin. Okay, it will depend on underlying data generating process and its functional forms, but under many forms, it probably will be robust to dropping those units at the heaps. So the donut hole, what you're going to do in the donut hole is you're just going to drop. You're basically going to drop donut hole RDD drops the units at the cutoff and then estimates using the remaining data with a slightly larger cutoff window, because now it's C0 minus 1 and C0 plus 1 that you're using. Okay. So they do that. Dropping units always changes the parameter that we're estimating. So we're no longer estimating the average treatment effect at the cutoff. We're estimating an average treatment effect that's, a little bit further away from the cutoff. But in this case, dropping at the threshold reduced the sample size by 2%. It allows for the possibility that the units at the heap differ markedly due to selection bias. Donut hole analysis found effect sizes in this paper that were 50% smaller than what Doug Allman originally found. And so, it ended up mattering. It ended up mattering a lot. It looks like that Doug Allman paper may have suffered from some selection bias. So you have to be careful. You have to be careful with this heaping. Okay, so let's take another 10-minute break. We'll come back at 15 minutes on the hour. We're gonna take a 10-minute break, and we'll finish RDD. We'll finish regression we'll finish today with regression discontinuity as best we can. Hopefully we'll finish. If we don't finish, we'll finish tomorrow. All right. All right. See you in a minute. All right. So let's go back to regression discontinuity. So we discussed all these issues around manipulation, but it could be that, even though you don't have like manipulation, it could be that even when you hold fixed the cutoff, it still could be that the treatment is endogenous. What does endogeneity mean? here? Well, endogeneity means two things. One, endogeneity of the treatment in an RDD situation just means that smoothness won't hold. Okay. So it just means smoothness won't hold. But why? Well, it could mean something else happened at that cutoff other than the treatment. So even if the treatment hadn't occurred, something else would have impacted the person at exactly that point on the running variable. Okay. So but some of these are actually testable since they involve other outcomes that we might examine. Okay, so let's look at that. So examples of endogenous cutoffs, maybe in the United States, age 65 is when you become eligible for universal health care. But age 65 is when a lot of people will retire too. And so maybe even if they hadn't become eligible for universal health care, maybe they would have, still retired. And in doing so, had some other similar events happen. People will use, this happens a lot with age thresholds. So when you have age thresholds that are being used for cutoffs, if those ages are special, other things could be happening at the same time, okay? Some of these can be weakly defended with balance tests or maybe directly testable through placebos if you have the data. So evaluating smoothness through balance is essentially going to be trying to test for smoothness by looking at covariates that are highly predictive of the outcomes. So let me give you an example. So here's from a paper that we're going to discuss. In this paper, you've got a running variable called democratic vote share. This is the share of all votes that went to a particular candidate in the Democratic Party in the United States. And this is income for the jurisdictions. This is basically like a small jurisdiction of voters. Small jurisdiction of voters. You can see right here that in places, this is, it's a collection, several, it's grouping many different jurisdictions. No. Okay, so it's grouping many of them together. So you can see right here, those places, so in the United States, in the USA, we use majority rules for determining who wins an election. So if you win vote share greater than 0.5, you are considered the winner, right? So they're going to use in this study that we're going to talk about in a second, close elections as their identification. Okay, so what we get is, but they're trying to evaluate whether odd things happen at places that barely win by looking at the characteristics of those areas. All right. So they're going to look at income, the share of the population that graduated from high school, the share that's eligible to vote, the share that's African American. And you can see right here, that there is a bit of a jump, but the standard errors are large enough that the confidence intervals encompass both, each other. So these are not statistically different from each other. These are not statistically different from each other. These are not statistically. These are not statistically. So what this balance test did, these are versions of balance tests that you might see in an RCT table. It's covariates that are highly predictive of outcomes and checking whether those covariates themselves break at the cutoff. But here, they don't. It's not a test for smoothness, because smoothness involves unobserved potential outcomes, so you can't test it directly. This, rather, is the sort of testing that economists often do, which is an indirect test based on their understanding of the sorts of things that predict victories and ultimately the behavior of legislators. Okay, that's what it is. Nothing changed. So here, all four covariates are balanced in the sense that you cannot reject the null at the cutoff, of no effect at the cutoff. You can also do placebos. Placebos are very common in quasi-experimental work. Excuse me. Placebos are very common in quasi-experimental work. And what people will sometimes do is choose artificial points in the running variable where there is no treatment assignment and just repeat their analysis. And so this kind of placebo-like approach where you're choosing non-discontinuous points, it's got the same flavor as the kind of things we're doing with randomization inference. We're just kind of imagining treatments where there are none. All right, so let's look at the kinds of evidence now that we've gone through all these issues. What exactly should your paper include? It will include a lot of pictures. Synthetic control and regression discontinuity design are very, very similar in that both of them have a lot of pictures. There's eyeball tests that are very, very common. An eyeball test is basically just viewing the picture and seeing whether or not you find the picture convincing on its own. Those are extremely common in regression discontinuity design. Even if your main results are parametric, you'll still want to present at least some pictures according to Embens and Lemieux. So let's review some of the graphs that you have to include. One, you have to include a graph of the outcome by the running variable. You're going to have to put the outcome into bins, average the outcome within bins on both sides of the cutoff, look at different bin sizes. You're just going to be plotting y as a function of x on the horizontal axis, and you're just going to probably have a flexible regression line on top of the bin means, something like this, right? So this is a mandatory, this should be one of your main results. If a person can't see the jump at the cutoff, they are likely to find anything else you do as non-credible. But here, the jump is visible, so you are likely to have people willing to consider that you've identified causal effect so long as all the other checks are done. Okay, so here, this is with around 5. This is with bins of around I think 0.02. Let's see bins even smaller. All right, so this is probably bins of 0.01 or 0.005. So smaller bins doesn't really change the finding, but does change the presentation. You should be choosing a binning here that is either based on some optimal binning procedure from software, or that you consider to be the best one that fits with the project you're involved in. Okay, so maybe if you're using certain bins throughout the whole thing, make sure that be the bin that you're presenting here. If there is a first stage, you want to show the probability of treatment like Mark did. This was, not an outcome. Notice this is not the outcome. Outcome was earnings. This is the first stage. It's the effect of the cutoff on enrollment. It shows that the probability of treatment jumps at 0. Okay, show that. If you have treatment data, definitely show it, because imagine Mark had only shown the graph for earnings, right? But he never showed this graph. And then one day someone shows a graph like this one, and there is no jump at 0. Wouldn't that mean Mark's findings on earnings were wrong? The only way there is an effect on earnings is if there is a jump at 0 in treatment assignment. So having both can reinforce the credibility of the study. Density test, have to show that, that's mandatory. Balance pictures, show things like that. Now we move into how do we construct some, how do we construct confidence intervals? How do we handle weighting procedures? And how do we choose our bandwidths? So Lee and Card and Lee and Lemieux in 2008 and 2010 recommended clustering standard errors on the running variable. But Colsair and Roth provide theoretical and simulation-based evidence that this is not good practice. You'd be better off with just heteroscedastic, robust standard errors. So they proposed 2 alternative confidence intervals that achieve correct coverage in large samples. They call these honest. I really encourage you to read the paper. I believe, let's look here. There it is. Colsair and Roth. I really encourage you to read it, because the first 4 pages are a really great writing. And if you want to see an example of just excellent writing, for an intro, I highly recommend it. Use the residualized outcome. No, I think that the residualized outcome, isn't a substitute, Sasha, because the residualized outcome is still not going to tell us that there was a change in treatment status. It's just going to tell us that, good grief, that was a mistake. All right. It's just this is a residualized outcome. All it's going to do is tell us there's a, there may or may not be a jump at 0. But if you were to show this, and let's just imagine that you were to do this and the data had looked like this, right? Okay, if you had done something like that, then you would have to conclude cutoff doesn't have an effect on enrollment, right? Doesn't have an effect on enrollment. And so if it's not having an effect on enrollment, well then if there's no effect on enrollment, then how do I interpret this gap? It can't be the effect of enrollment because there was no effect on enrollment. Balance plots are useful to check for potential confounders. Yeah, balance plots are useful to check for potential confounders. Hunger balance plots are useful to check for potential. Yes. Yes, that's right. Sasha says, aren't we assuming smoothness conditional on covariance? We are, but we are assuming it. We are assuming it. But my point here is that you have to build the case for smoothness. You can't just take it for granted and hope that the reader finds it believable without any evidence for it. So you need to show that something changed. You need to show that treatment changes at the cutoff. If treatment doesn't change at the cutoff, then why should I believe smoothness is holding for your main outcome analysis? Smoothness is saying, absent the treatment, the potential outcomes would have evolved similarly. And if there is no change in enrollment, if there is no change in treatment at C0, then it logically means the estimated effects on an outcome cannot be due to the treatment because the treatment didn't change in the first place. This is why you have to present evidence for treatment assignment changing at C0. That if you don't have data on treatment assignment on treatments, which you sometimes don't, then you need to just show the documentation from the program saying treatment occurs at C0. Correct. Yes. So it has mean zero. You mean the residuals has mean zero? Is that what you're saying, Angelica?
Yes, residual has, when we estimate that model that you showed us, it will minimize the residual. So it has OLS assumes constant variance and the expected value of the error term is 0.
Okay. Okay. I hadn't thought of it that way. I have to think about that. That sounds correct to me too. So they're going to propose 2 alternative confidence intervals, Colasar and Roth, that you use instead of clustering. So you don't want, you know, Colasar and Roth 2018 AER show that clustering on the running variable is the worst solution for inference. They then present new confidence intervals that are robust, called honest. And that is available in R from GitHub below. Okay, so you can implement this you can implement their correction using using the RD honest command, and that will give you confidence intervals with correct coverage, 95% coverage. Cadeneo is an alternative paper to that Hahn, Todd, and Vanderklau smoothness paper, and they say if you want to do inference, you can also do randomization inference. You just have to assume that the cutoff is a randomized experiment. And if it is a randomized experiment, that some units are just being randomly, pushed to one side or the other of the cutoff, which for many applications does seem like that could probably be true, just because of the sheer amount of noise that goes into, the effort that we make, then we could use randomization inference, which is a test of the null of no individual level treatment effects. So we've got these least squares approaches, right? It's kind of backing up for a little bit. If you remember from earlier, we said pth order polynomials to handle nonlinearities, and I said kernel methods. Okay, we did pth order polynomials. That's the least squares approach. It models explicitly using functional forms. It is parametric. It's parametric. Hold on one second. Sorry, it was a little loud downstairs. But because it's parametric, because it uses functional forms, it actually has poor predictive properties on counterfactuals if those functional forms are incorrect. So, it can suffer from bias because it is parametric if the functional form is misspecified, right? So another way of doing it is to use a non-parametric kernel. It has its own problems, just not that problem. Got a little cat here that wants to get up here with me. So let's look at that. So let's look at this this situation here. What we have here is potential outcomes, right? So here we have potential outcomes. Okay. Now in this range right here, it's observed. And that's because up here, d equals 1, and down here, d equals 0. So, when d equals 0, we observe y0. And when d equal 1, we observe y1. Okay. We don't observe this part. Unobserved. We don't observe this part. We don't observe this part. Right? So we're wanting to estimate this right there. That is our treatment effect parameter target, right there. So we're wanting to get this, all right? But if we use just like a histogram, if we use just the averages for a certain bin, I just call it, the averages for certain bins, that's a histogram, I guess. If we were to use like, this and this, well, then we would be estimating a gap that big. It would be too big. So if we use that bandwidth, then given the trends in the data, it will yield a biased, slightly biased estimate of the true causal parameter, AB. Okay? That's if there's trends. So the non-parametric one-sided kernel estimation problems, it's basically histograms. They're called boundary problems at the cutoff because when you draw this right here, when you draw this right here, you know, that boundary right there is creating this bias because it's cutting through the trends. It's cutting through the trends, you know, taking some average value for the entire thing. Okay, so we're basically just, you know, taking averages, and the tops of the rectangles are suffering from this boundary problem. So kernel estimation can have poor properties. So they propose using regression, local linear non-parametric regressions. Local linear non-parametric regressions substantially reduce the bias. Think of it as a weighted regression restricted to a window. Kernel provides the weight to that regression. Okay, so what we're going to do is we're going to run this regression with weights around the units closest to the cutoff being weighted the most. Let me show you what this looks like. So this is a local linear regression. And what you're basically doing with a local linear regression is you're fitting regressions using lots of data. Notice, okay, okay, so notice, let me do it again. Right, so notice all the data that's being used, and you're fitting the lines through those data. Okay, so you're using some window that's evolving over time. All right, so you can use that. That was not a regression discontinuity example. That was just local linear regression. But the poly command in Stata will estimate kernel weighted local polynomial regressions. Now, a rectangular kernel will give the same result as just taking the average, but a triangular kernel will give more importance to observations close to the center. And this method, all right, so basically just a couple of things to say about this. The number one, rectangular kernel is just taking averages for a bin around X. Like a unadjusted, an unadjusted histogram. It weights all units the same. The triangular kernel gives more importance to observations close to the center, and as a result of that, can tilt so that you don't have that boundary problem. And then three, you still have to pick the bandwidth, right? In that animation, the bandwidth was chosen. Different bandwidths, different regression lines. Okay, so what we will see are estimators that do one and two, that do two for us, and even pick optimal bandwidths for number three, so that you aren't picking them on your own. It'll be a data-driven procedure. Hold on 1 second. Come on in. What, Betty? Betty. I have one cat that comes in and then immediately the other one goes out. So it's going to be a big pain. So several methods that exist for choosing that bandwidth. Again, what was the bandwidth? Here, that was the bandwidth. All right. It's the amount of data that you're going to bring in to do your analysis, right? You're not going to use all of it. When we were running those regressions, we had no bandwidths. We were using all of the data. We were just fitting functional forms. Now what we're doing is working with bandwidths. And then picking that bandwidth is all about, living with trade-offs between the bias associated with the analysis and the variance associated with the analysis. So in practical applications, you want to check for balance around that window. And the standard error of the treatment effects, they can usually be bootstrapped. The software that is done can do the bootstrapping for you. You could add in other variables to those non-parametric methods if you wanted to. So there's two historical papers that what they do is they estimate how big that should be. Should it be this big? Should it be this big? Should it be this big over here, but this big over here, right? Like, so it allows for lots of different data-driven sizes to the data set to create those bandwidths. And the first one was by Hito Embens and Cal Umarin in the Review of Economic Studies. And then more recently, there was a paper by Kolonenko that was in Econometrica. They both proposed methods for estimating optimal bandwidths that can differ on either side of the cutoff. Kolonenko proposed local polynomial regression discontinuity estimators with robust confidence intervals and rolled out a piece of software called RD Robust that was available in Stata and in R. Okay, so I've got 10 minutes. I think that what we should do is stop there because the next section for RD is coding, and I have to go through a paper to kind of explain what we're going to be doing. But if I do that now, I think that it won't be as fresh tomorrow. It won't take us very long. It won't take us very long to cover it, but I just want to do it all at once. So let's just have some questions and answer. Okay, so Melba, can you rewrite that question? I think it got cut off. Let me let my cats in while you're writing it. Can you rewrite that question, Melba? I don't think I understand it. And okay, if you're designing an RD study ex ante, how would sampling be affected? Do you want to sample globally, or you want to sample globally? You would like to, usually you're wanting as much data as possible because you're trying to do inference right at the cutoff. If you're doing any of that functional form, kind of pth order polynomial modeling, you're going to need a lot of data, period. Most of the analysis leverages all of that data outside of the treatment window just for power. The most robust ones are still able to incorporate it using things like, triangular kernels and things of that nature. So they'll still bring in that data, but the inference will be really focused on stuff right at the cutoff. So you really want to have large samples. Yes, Holger, the honest CI is going to be confidence intervals for the estimated treatment effects. Correct. So if you want for tomorrow, does the literature, yeah, Melba, that's a really good question. This is where the art and the science of regression discontinuity design are not completely aligned. Papers still will, let's see if I can't find this paper. Here we go. Okay, So let me show you this paper right here. So this is a paper similar to one that we're going to discuss tomorrow. It's called Political Parties and Labor Market Outcomes, Evidence from the United States. What they're going to do is they're going to use close elections in our governor races. Governors are the head executive office of an entire state. So we have 50 states. We have 50 governors. They're going to use governor races from 1977 to 2008, estimating the effect of a Democratic win on racial earnings gaps between Black and white workers. Okay, so it's going to be a regression discontinuity design. They're going to have global regressions. Here's a global regression right here. They're going to do this kind of slightly different sort of specification, but here's the governor wins, and the governor wins, and it's an African-American respondent. It's going to be using individual level data. So they've got a dummy for whether the individual is African-American and a dummy for whether the governor, the Democratic player wins. Put in a bunch of controls, put in Z, what is Z? State fixed and year fixed effects. X is individual characteristics. Here's the pth order polynomials right here. So this is the running variable. It is margin of victory. So it's how much they win by. And so here is the running variable and FB, I think that's, oh yeah, FB is African-American interacted with the running variable. They're going to allow for, I think, polynomials. Okay, so this is a global regression. Okay, it's global regression. Therefore, you'll have to focus on FMV as polynomials. So what do they do? All right, descriptive statistics, I'll skip that. Here's some pictures, like I said, main results. So notice what we've got for main results. We've got right there. For Black workers, you've got an increase in working for African-American workers. If a Democrat governor wins, you see nothing like that here. Okay, so all right, these are main results. They lead, their first figure are their main results, and it's a picture, right? So that's first thing. What about when they actually, so then they've got their more evidence here for hours worked. You still see the effect for African-Americans, see nothing there. Now we have our main results. Look at what they're going to do now. They're going to go through and produce not just figures, but the the parametric models. Down here, you see it. Controls are age, H2, H3, H4. See, they don't really mention what they're doing with the polynomials, but you've got here, this is this right here, this Democrat Black is their variable of interest. You see here effects for men. So the effects appear to be driven for men. They just keep exploring what exactly is going on, but then they have a validity, robustness, and heterogeneity section. Okay, so a lot of this they end up putting in the appendix, they said. So let's see what we get. Appendix. RD without covariates. RD for earnings. Now we're going to be looking at discontinuity in baseline covariates. All right, so here's our balance stuff. RD estimates for outcome at a different period in time. All right, so more placebos. RD estimates at a T-1 placebo test. This is that Lee and Lemieux. They're redoing it at different points in time, showing results then. Nothing, nothing, nothing. They do different bandwidths. Now they're moving away from the global regressions, and now they're using these non-parametric methods. Here you see the Embens and Calumarin. Here you see that Calanico, Cadiano, and Tatunic. different bandwidths that are now being artificially chosen themselves to see how robust their results are. These are placebo tests. Different specifications for state level regressions. Just goes on and on and on. So what do they do? To answer your question, Melba, they do both. So how do you generate the exact distribution if you do randomization inference in the context of an RDD design? What you would basically have to do, Holger, is you would have to find a bandwidth and then essentially assign. So you've got groups that you know are in the treatment, and you got groups that you know are not in the treatment, and you just pretend that units are in the treatment or control. You go through every single combination, or you use that simulation. You can either use, you can manually code it yourself. I have code in the mixtape that will manually code randomization inference. There's other programs that will do it automatically, but essentially what you would be doing is just assigning treatment and control using that Fisher assignment, getting coefficients, and then using the distribution of the coefficients to get a p-value. And there is also a way to use randomization inference to get confidence intervals. So you would have to do that slightly different modified randomization inference to get the confidence intervals. Correct. Angelica says, so RDD data is not limited to cross-section. That's correct. It's not. It can be pooled cross-sections over time. It can also be in time. Didn't get the placebo test. Placebo test? You mean those balance tests, or do you mean the placebo in the placebo along the running variable? This is the placebo along the running variable. So let's say that we have kind of noisy. Okay, so you've got this like clear discontinuity here, but what if we were to do this? What if we were to make placebos here, here? Okay, so what are these? These are both the median from 0 to C0. This is C0. This is like, X bar. And so this would be median from C0 to X bar, right? And these are both placebo discontinuities. Placebo discontinuities, okay? Well, there is no treatment assignment at these medians. So if you do this analysis and you find similar results using a false discontinuity, calls into question the validity of your original analysis, right? Could be the data is so noisy, you find gaps everywhere. In other words. So placebos, so with placebo analysis, you pick fake, you pretend discontinuities and repeat your analysis for those, hoping to fail to reject the null at those other two medians, Lee and Lemieux. I think it's 2008. Okay. Okay. I thought that was productive. I hope that was helpful. Hopefully tomorrow, when we go into the code, we'll have a better sense about, mechanically exactly what we mean by global regressions and local regressions and figures and how to make the figures, and just get through the nuts and the technical details of actually doing it. so that when you begin to do these projects yourself, you'll at least see a small roadmap that can help you get started. You're welcome, Angela. Okay, you guys have a great day, great evening, and I'll see you tomorrow. Goodbye.
Thank you.